Hello everybody, this is Dr. Bricker here with a Homework 3 help video. So the first question is, the charge carriers in metals are, and I'm not going to give you the answer, but you can take a look back at this part of the book, click the review part to go through here. So which particles are free to move in metals? That's another way of rephrasing this question. Okay, next one. When a nerve cell depolarizes, charge is transferred across the cell membrane, changing the potential difference, or in other words, voltage. For a typical nerve cell, 0.9 picocoulombs, so what is a pico? Times 10 to the minus 12. So 9 times 10 to the minus 12 charge flows in 0.5 milliseconds. What's a millisecond? Times 10 to the minus third seconds. What is the average current? So the current is the amount of charge divided by the amount of time. Just be careful with the units here. So you'll have 9 times 10 to the minus 12 coulombs divided by 0.5 to the minus third milliseconds. And then they want the answer in nanoamps, right? Coulombs per second, that's what an amp is. You just have to put it into nanoamps. So how many times 10 to the minus ninths do you have there? Okay. Good. Moving on to the next one. A wire carries 15 microamps. So what is a micro? Times 10 to the minus sixth. How many electrons pass a given point in 1 second? Okay, let's take a look at this one. Okay, so we've got 15 microamps. So we've got 15 times 10 to the minus sixth amps. And an amp is a coulomb per second. And then we could multiply it by 1 second. This will tell me how many coulombs I have. So 15 times 10 to the minus 6 coulombs. I mean, they could have given us 30 seconds or more, but I'm just going with what they gave me, 1 second. So that's how many coulombs. And then don't forget the magnitude of charge from 1 electron. 1.6 to the minus 19th coulombs. Grab my calculator here. So 15 to the minus 6th, 15 EE, in other words, minus 6th, divided by 1.6 EE minus 19th, about 9.4 times 10 to the 13th. So, 10,000 billion or something like that, electrons. So a big amount. You could put the whole thing in 9.375 to the times 10 to the 13th if you wanted to. Okay, let's look at the next one. Okay, so this one, the fourth one in the homework, the unspecified currents in this figure are 6 amps. You might have different numbers, by the way, than this. IA is 6, and ID is 3. And we want to know a few other things here. How much is IC, and how much is IB? Okay, so this is Kirchhoff's junction rule type problem. The amount of current entering a branch has to be equal to the amount of current leaving the branch. Okay, so here's a branch point here. So 7 amps is coming in, 7 amps has to leave. It just splits up. So here they're telling us this is 6 amps this way. IA is 6. So IC then must be 1, right? I mean, because 6 plus 1 is 7. So IC's got to be 1. Okay, so IC is 1. ID is 3. So if you got 1 and you got 3 coming in, that's a total of 4. 4 has to leave. So IB is going to be 4. Okay, and this is all measured in amps. Okay, you've got different numbers probably, so maybe not though. So, take that into account. Okay, not so bad. The amount of current entering a junction is the same amount of total current that has to leave a junction. Next one. 9.5 volt battery supplies 2 milliamps to a circuit for 3 hours. So don't forget, an amp is a coulomb per second. So if you're wondering how time is going to factor in. How much charge has been transferred from the negative to the positive terminal of the battery in coulombs? And then how much electric potential energy has been gained by the charges that pass through the battery? Okay, so the battery's through chemical means turning chemical energy into potential energy. How much do we have? Let's take a look at this one. Okay, so the voltage of the battery, that's the squiggly E, 9.5 just volts. Current 2 milliamps, so milli means to the minus third, for 3 hours. How much charge does that correspond to? Okay, so don't forget the current is the amount of charge divided by the time. So then the amount of charge multiplied both sides by T, I times T. So we've got 2 times 10 to the minus third, an amp, but don't forget that's a coulomb per second. And then how many seconds do we have? Well, we have 3 hours, so we got to turn that into seconds. 1 hour is 3,600 seconds. You could say 1 hour is 60 minutes, and then 60 minutes, 1 minute is 60 seconds. That's where I'm getting the 3,600 from. Okay, so as far as the units go, the hours cancel out and the seconds cancel out. And this will give you how much charge you have. I'll leave it to you to punch that in. Again, you might have different numbers too. So that's how to get the total charge. And then once you have the total charge, this is part A. Part B is how much energy does that correspond to. So the amount of energy we have is equal to Q times delta V. This really goes back to the previous chapter. Okay. The voltage, we're just calling it squiggly E, though maybe that's the part that's a little bit different. So you have to use the charge from the first part, and then multiply that by the voltage. That'll give you the amount of potential energy that has been turned into electrical potential energy from chemical energy. Okay, good. Let's look at the next one. Okay, so resistivity measurements on the leaves of corn plants are a good way to assess stress and overall health of the plants. So the leaf of a corn plant has a resistance of 2.2 mega ohms. Mega is times 10 to the 6th, million in other words. Measured between 2 electrodes that are placed 20 centimeters apart on the leaf. The leaf has a width of 2.5 centimeters and is 0.2 millimeters thick. I mean, if you think about a leaf, it's not a uniform shape, but we're assuming it's got these dimensions. 2.5 centimeters wide and 0.2 millimeters thick. So we can get a cross-sectional area from that. And you can take a look at the video tutor solution here. From this, we want to know what is the resistivity of the leaf, and is it greater than or less than the resistivity of muscle tissue in the human body? Well, you'll have to get the answer for this part, measured in ohms times meters, and then compare it to the resistivity of the human body. And there's a table in the chapter. If you hit review, you can take a look at the table. Okay, so how are we going to calculate the resistivity? Let's take a look at this. Okay, so here's the resistance formula and how it depends on resistivity. So R is the resistance, measured in ohms. This is the resistivity. So if you remember from this chapter, chapter 22, the resistivity really goes back to what it's made out of, related to temperature as well, but this is the idea that silver has a lower resistivity than, say, copper. Muscle has a lower resistivity than fat, so it's just a property of whatever the item is made out of. L is the length, and then A is the cross-sectional area. So we use this formula in the notes to look at just a wire, where this is the cross-sectional area, this is the length. In this problem, we're going to apply this to a leaf, and we're going to assume a leaf has this kind of shape, where this is the length, and then the cross-sectional area is the width, 2.5 centimeters, times the height, 0.2 millimeters. Okay, so the whatever electrodes are placed, maybe something like here, and you're measuring the resistance across the leaf. That came out to be 2.2 mega ohms. So we can work backwards and figure out the resistivity then. So from this formula, R times A divided by L is the resistivity. So R is the actual resistance, 2.2 times 10 to the 6th ohms. The cross-sectional area would be this, be careful with the units. So they gave us 2.5 centimeters, so 0.025 meters times this 0.2 millimeters, 0.2 to the minus third meters. So resistance, this is the area, that's what this term is, and then divided by the length. And the length they give us in the problem, 20 centimeters or 0.2 meters. So you have to get all that together. You'll see it'll come out in ohms times meters. Okay, and you might have different numbers too, so be careful with that. This is a good example though. You know, we've got millimeters, centimeters, all floating around. We've got to put them all in terms of meters. And then you see meters times meters, that's meters squared divided by meters, leaves us with meter here, and then we still have the ohms. Okay, who would have thought you could see if a corn plant is healthy by using Physics 221 and resistance. Let's look at the next one. Okay, so the femoral artery is the large artery that carries blood to the leg. A person's femoral artery has an inner diameter of 1 centimeter. For the steps and strategies in a similar problem, you can again take a look at the author of the book working something out like this. What is the resistance of a 20 centimeter column of blood in the artery? Assume that the resistivity of blood is 1.6 ohms times meters. Okay, so this is more of a straightforward application of our formula for resistance and resistivity. So remember, the resistance, R, is equal to the resistivity, rho, times the length of the, whatever it is. The length here is 20 centimeters, divided by the cross-sectional area. So we're going to assume that this femoral artery is the shape of a cylinder. So you have to get the cross-sectional area of this artery. So think of it like a wire. So the cross-sectional area of a circle is pi times the radius squared. So the diameter is 1 centimeter, so the radius would be 0.5 centimeters, and then turn it into meters. So it's more of a straightforward application of that formula. Resistance is equal to resistivity times the length divided by the cross-sectional area. And you have everything here to put it together. We're not using a wire, we're using a column of blood in this artery. Okay, and you can review that section again. Let's look at the next one. Okay, so here's a graph. Whenever you see a graph, what's being graphed? Current versus voltage. Amps versus current in amps versus potential difference in volts. What is the cylinder's resistance? Let's take a look at this. Okay, so from the graph, I just read this. At 100 volts, the current was 2 amps. That's from looking at the actual graph. Here's the formula for how voltage and current and resistance are all related to each other. So delta V is equal to I times R. So R then is delta V over I. So you can pick any point you wanted on the graph. I just picked a convenient point where this was 100 volts, this was 2 amps. So put it all together, we have 100 volts divided by 2 amps, which that's what an ohm is. And we get 50 ohms for this. Okay, let's look at the next one. Okay, so this is kind of a transitional problem where we're looking at electric fields and voltages together. Usually electric fields are separate from when we think about it anyway. Electric fields are one way of looking at a problem, voltage is another way of looking at it. This one kind of combines these together. This is kind of similar to the lab that you did with this concept as well. Electric field inside a 60 centimeter long copper wire is 0.011 volts per meter. What is the potential difference between the ends of the wire? Okay, let's take a look at this. Okay, so from the chapter, and really this goes back to the previous chapter as well, the voltage potential difference is E times the length. And they give us the actual length here. It's 60 centimeters or 0.6 meters. Here's the electric field strength. So if we take 0.011 volts per meter, multiply it by the length that we have here, 0.6 meters, that will give us the answer in volts. So remember, electric field can be measured in volts per meter. That's how we've been looking at it recently. Or newtons per coulomb, those are equivalent units. Okay, let's look at the next one. On a sunny day, a rooftop solar panel delivers 60 watts. Okay, you have to ask yourself, what a watt, what is that measuring? That's power. Actually, it says of power. Okay, good. So 60 watts of power to a house at a voltage of 17 volts. So EMF means electromotive force, historically. It's also voltage. So when you say EMF, squiggly E, that's what voltage is. And you can tell by the units here, right? V for volts. How much current flows through the panel? Okay, so we know that the power is equal to the current times the voltage. Here we know the power, and we know the voltage. You just have to solve for the current. So P is equal to I times V. Okay, not too bad. And the last one, when running on its 11.4 volt battery, a laptop uses 8.3 watts. Okay, so that's a watt is a joule per second. That's how much power we're using. The computer can run on the battery for 8 hours before the battery is depleted. What is the current delivered by the battery to the computer? And then how much energy is the battery capable of supplying? Okay, so 8.3 watts, this is 8.3 joules per second. And it can run for 8 hours. So it's probably easier to get part B to begin with, actually. 8.3 watts, so 8.3 joules per second, multiply it by how many seconds you have. You'll have to turn this into seconds. And that'll give you the total amount of energy that is supplied by the battery. Okay? So power times time gives you the amount of energy. The first part, what is the current delivered by the battery to the computer? Okay, so that's sort of what we did on the previous problem. This is 8.3 watts. That's the power. Power is equal to current times voltage. Here they give you the power and the voltage. You can solve for the current. So the current is the power divided by the voltage. Okay, good. So this is kind of a springboard chapter, this chapter 22, into the next chapter where we actually analyze some circuits. Okay? Any questions, email me, and I'll talk to you soon. Bye-bye.